And welcome to the second session of chemical equations. Before we start discussing what we would be studying in this session, let us first recall what we studied in the previous session. We studied about two changes that take place in our daily life and their classification. One being a physical change, a change in which no new substance takes place, and if you reverse engineer the conditions, then you can get the substance back. For example, melting of wax. When you light a candle to melt some wax, then if you reverse engineer the condition and you cool it down, what you get back is wax and not any new compound. So melting of wax is a physical change. A chemical change is a change in which new substance forms from pre-existing ones. Two substances or more substances come together, go under a chemical reaction, and a new compound or a new substance is formed. For example, if you burn a magnesium ribbon in air, it turns into ashes. Even if you reverse engineer the conditions and even if you take all the heat back, those ashes cannot go back to being a magnesium ribbon. Hence, the burning of magnesium ribbon in air is considered a chemical change. Normally, chemical changes are either endothermic or exothermic. Endothermic means these reactions or these changes, they absorb heat. Exothermic means these reactions or these changes liberate heat. Sometimes these chemical change may cause a change in state of a substance. From a solid state, it may turn into a liquid state. From liquid state, it may turn into a gaseous state, or from a gaseous state back to liquid, back to solid. Chemical changes can cause a change in state. Usually, chemical changes also change the characteristic properties of that substance. If you mix a certain substance with certain other substance, the resulting substance may be of a whole different color. Sometimes chemical change also lead to formation of a residue or a precipitate. For example, if you mix barium chloride with sodium sulfate together, then when this mixture is stirred and is let to be, then a precipitate of barium sulfate is formed. It is a white precipitate or a white residue. Hence, there are a lot of changes that can be caused due to a physical change or due to a chemical change. Now, the symbolic representation of a chemical reaction using chemical formulae of compounds and symbol of elements involved in the reaction is called a chemical equation. So, a change where two or more reactants react together to form a product is called a chemical reaction. If you were to represent this chemical reaction in some form by writing, you can either use something called a word equation or something called a chemical equation, that is the symbolic representation of the word equation. Elements that undergo the reaction are called reactants, and elements that are formed at the end of the reaction are called products. Reactants are written on the left hand side and an arrowhead points in the direction of the product, which goes on the right hand side. All chemical equations obey the law of conservation of mass, which means that number of atoms of each element on each side must be same. Why? Because atoms can neither be created and atoms can neither be destroyed. Hence, all chemical equations must be balanced. And chemical equations need to obey the law of conservation of mass. Let us now come to what we will be studying in this session. We will again define what a balanced equation is. We will, through different examples, try and study the steps of how we balance a chemical equation. Before that, we will study some other concepts that involve and are related to balancing a chemical equation. Then we will try and balance different chemical equations and make a summary of whatever we studied in this session. So without any further ado, let's get started. All chemical equations must be balanced. A balanced chemical equation is an equation in which the number of atoms of each element is same on the reactant side and on the product side. Since atoms can neither be created nor they can be destroyed in a chemical reaction, we say that all chemical equations must be balanced. A chemical equations in which the number of atoms of different elements on the reactant side, that is the left side, are same as those on the product side, which is the right side, is a balanced chemical equation or a balanced reaction. It is important to remember the definition of balanced chemical equations. What separates the reactant from the products is the arrowhead or the direction in which we point, which is the formation of the product. Let us now go to what is needed to balance a chemical equation. The first concept that we study is a formula unit. Balancing a chemical equation involves finding out how many formula units of each substance take part in a reaction. Formula unit means one unit, a symbolic representation maybe of a compound, of an element, of an ion, or of an atom. That is one formula unit. So, one formula unit of NaCl has one sodium ion and one chlorine anion, Na plus and Cl minus. The formula unit of MgBr2, magnesium bromide, is having a magnesium 2 plus cation and a bromine anion. That is how we define formula unit. Formula units are defined also by something called concept of valency, which is important to understand before we begin balancing our chemical equations. Even though you must have studied about valency in your previous classes, let me remind you that valency is the combining capacity of an element. It depends on how many electrons a particular atom can lose. Why do atoms lose electrons or gain electrons? It is to become more stable. You will study about these stabilities in later classes. All we have to know right now that in an atom, it's in its stable most state when we just refer to it as an atom without referring it to it as an ion, a charged one, has some amount of electrons and has some amount of protons. We know that the number of electrons and protons are same in an atom, and hence the charge on an atom is balanced. But when an atom gives away one or more electron, it forms something called as a cation. For example, if you take away one electron from sodium, then the number of protons in sodium will increase, and it will increase by 1 since sodium lost one electron. So we represent this particular atom as Na plus since sodium becomes charged by 1. You don't need to write plus 1, you can only write plus to denote that it is charged by 1 since it lost an electron. If an atom gains one or more electron, it forms an anion. Since it gains one or more electron, we know that the number of protons and electrons in an atom are similar. Electrons are negatively charged and protons are positively charged. If an atom is gaining an electron, it means it is gaining negative charge. So, if it gains one electron, we say the negative charge increases by 1. For example, when chlorine atom gains one electron, it becomes negatively charged, and by 1. To represent it, you can use Cl and on the top right hand corner a minus symbol. This is how we define the concept of valency. Let us now discuss different kinds of ions. An ion is a charged atom or a molecule. So, there are two types of ions. Either they are cations, cations are positively charged ions, or either there are anions. Anions are negatively charged ions. So, monovalent cations or atoms which give away one electron and become positively charged by 1. For example, sodium ion, potassium ion, hydrogen ion, or ammonium ion. The examples that I have provided to you. If you look at the diagram that has been presented to you towards the left hand side, you see that sodium atom in its normal state without being charged has 11 electrons. And once it loses its outer electron from the outermost shell, it has 10 electrons now and it forms a sodium ion. The sodium atom, when it loses an outer electron, it forms sodium ion. Now, monovalent anions, atoms which take one electron, are forming monovalent anions. Means they are negatively charged by one. Mono means one. Examples are fluoride ion, bromide ion, chloride ion, iodide ion. These were monovalent ions. Now let us talk about divalent ions. Divalent ions are also of two types, divalent cations and divalent anions. Divalent cations are atoms which give away two electrons. If they give away two electrons, then their protons are now two more than the electrons. Hence, they are positively charged by 2. So, we can represent them by writing the atom's name and 2 plus at the top right hand corner of the atom. Example, calcium, magnesium, manganese, zinc, lead. Lead has a symbolic representation of Pb. All of these usually lose 2 electrons to become positively charged divalent cations. Now, divalent anions. Atoms which take 2 electrons to become negatively charged by 2 or increase their negative charge by 2 form negative divalent anions. The example is the oxygen atom, which gains 2 electrons to form oxide atom, sulfate ion, carbonate ion. All of these have a charge of 2 minus. If you look at the diagram that has been presented to you on the right hand side, oxygen atom has 8 electrons in its shells. When it gains 2 more electrons, it becomes negatively charged. The oxygen atom now becomes an oxide ion and it has 10 electrons in its shell. These were divalent ions. Let us now go to trivalent ions and elements that show variable valency. So, even trivalent ions are of two types, trivalent cations and trivalent anions. Trivalent cations are atoms which give away 3 electrons. The most common example of a trivalent cation is an aluminium ion. Aluminium ion usually has 13 electrons in its outer shells. It loses 3 electrons and now thus has only 10 electrons in its outer shell, and it forms Al3 plus aluminium ion, positively charged trivalent cation. Trivalent anions. Trivalent anions are atoms which gain 3 electrons. The most common example is the example of nitrogen, which gains 3 electrons to form the nitride ion. It is negatively charged, hence it's a trivalent anion. Phosphate ion also gains 3 electrons usually to become a negatively charged trivalent anion. What we just discussed were monovalent ions, monovalent cations, anions, divalent cations, anions, and trivalent cations and anions. Usually we saw that the atom loses some specific amount of electrons or an atom gains some specific kind of electrons, and that is described as its valency, combining capacity. Usually, there are some substances which show more than one valency. It means that sometimes they are ready to lose 2 electrons to become stable, sometimes they are ready to lose 1 electron to become stable. Sometimes those atoms gain 2 electrons to become stable, sometimes they gain 3 electrons to become stable. So it depends on what kind of atom or what kind of compound they combine with. All we have to know right now that there are some atoms of these elements, there are those that show more than one valency. It is called variable valency, and there are some atoms that show it. Two of the most common examples are copper. Copper sometimes has a valency of +1 and copper sometimes shows a valency of +2. So, one other example is that iron. Iron, represented by the symbol Fe, sometimes has a valency of +2 and sometimes it shows a valency of +3. Usually when it shows a valency of +2, it is called a ferrous ion, and when it shows a valency of +3, it is called a ferric ion. Same for copper. When it shows a valency of +1, it is called cuprous ion, and when it shows a valency of +2, it is called a cupric ion. Even though this information is not necessary to your level, you must remember that there are atoms which show variable valency. Since now we have studied what valent, monovalent, divalent, trivalent, and multiple variable valent atoms and cations, anions are, let us now go and write some formulae of some compounds before we start beginning to balance chemical equations. Writing chemical formulae. We will try and learn how we write chemical formulae, even though if you would have done it, by doing some examples. For example, take aluminium chloride. We discussed that aluminium has a it's a trivalent cation which has a valency of +3. Chlorine has a valency of -1. Usually when you're writing a chemical formula, it is always the cation followed by the anion and never the opposite. So what we do is we cross multiply their valencies and write it at the bottom. So if aluminium has a valency of +3 and chlorine has a valency of -1, when we cross multiply their valencies, we write Al1Cl3. Since 1 is something that is already understood and does not need to be written, we can write the formula of aluminium chloride as AlCl3. Let us now go to the next example. Sodium iodide. Sodium is a positively charged cation. Iodine is usually an anion. Sodium has a valency of +1. Iodine has a valency of -1. If you cross multiply both of their valencies, the compound that will thus form is Na1I1. We do not need to write the 1 as it is already understood. So the compound formula is thus results in NaI. Let us go to the next example. Aluminium sulfate. Now sulfate is itself a compound represented by the formula SO4 made of sulfur and oxygen. Now it has a valency of -2. We already know that aluminium has a valency of +3. So all we have to do to find the formula for aluminium sulfate is cross multiply their valencies. Now the formula that will thus result in Al2 SO4 in the bracket to separate the 4 and the 3, since SO4 is itself a compound, a separate compound. Therefore the valency and the whole chemical formula that is thus formed is Al2 SO4 thrice or 3. Now let us go to the next one. Barium chloride. We know that barium has a valency of +2 and chlorine has a valency of -1. Cross multiplication of these valencies will lead to the formation of the chemical formula Ba1Cl2. As I already mentioned, 1 is something that is already understood and need not be written again and again. So the resulting chemical formula is now written as BaCl2. I think now we are ready to balance some chemical equations. We will go step by step and understand how we write a balanced chemical equation and how we go about balancing a chemical equation. Some things to remember before we start balancing is that the ratio of atoms that is at the bottom is never touched and never changed. We can only change the coefficient that comes at the left of an atom or a molecule. That is the only thing that can be changed. Ratio of atoms written at the bottom is not changed while balancing a chemical equation. Step 1. We first write the chemical equation if it is not given to us. So if we say iron reacts with water to give iron oxide plus hydrogen gas, we will write the equation which will be as follows. Iron, that is Fe, plus H2O, which is water, it will give us Fe2O3, that is iron oxide, plus hydrogen gas, which is H2. Now, we know to balance the equations, we will not change the ratio of atoms at the bottom. That is the numbers 2, 2, 3 and 2. Those small numbers written as subscripts in the bottom. They are ratio of the atoms which we do not change. Step 2. What we do is we choose the element with the maximum number of atoms, either on the reactant side or on the product side. It does not matter for us. So, as of right now, you see that the atom with the element with the most number of atoms is oxygen, which is on the right hand side. So, we try and balance oxygen. How? We see that oxygen has 3 atoms. We need to have 3 atoms on the left hand side also. What we can do is right beside H2O, we can put 3 as the coefficient. This 3 acts as a coefficient of the whole molecule H2O and not just hydrogen in general. So now we have 3 atoms of oxygen on the right hand side and 3 atoms of oxygen on the left hand side. So now we choose the element which has the next maximum number of atoms, which for our case is hydrogen. We will try and now balance hydrogen. If you see, in step 2, we have around 6 atoms of hydrogen. The coefficient gets multiplied by the ratio of atoms. So 3 times 2 is 6. We have 6 hydrogen atoms on the left hand side and we only have 2 on the right hand side. What we can do is add a coefficient 3 to the right hand side and our equation becomes Fe plus 3H2O gives Fe2O3 plus 3H2. We now have to balance iron. That is the only element that is left to be balanced in our equation. Finally, we balance the next atoms by changing the coefficient of Fe. Since you see, Fe has 2 atoms on the right hand side and only 1 on the left hand side. So what you will do is add a coefficient 2 on the left hand side of Fe. And our equation then becomes 2Fe plus 3H2O gives Fe2O3 plus 3H2O plus 3H2. So this is how iron reacts with water to give ferric oxide plus hydrogen gas. Finally, we cross-check the equation by counting the number of atoms of each element on both sides. So let's do that. Let's take iron first. There are 2 atoms on the right hand side and there are 2 atoms on the left hand side. Let's check hydrogen. 3 times 2 is 6. Hence, there are 6 atoms of hydrogen on the left hand side. 3 times 2, 6. There are 6 atoms of hydrogen on the right hand side. Let's check oxygen. There are 3 atoms of oxygen as 3H2O. The 3 is for the whole molecule of H2O and not just hydrogen. Hence, there are 3 atoms of oxygen on the left hand side. As you see, it's Fe2O3. So there are 3 atoms of oxygen on the right hand side. The equation is hence balanced. This is the proper way of balancing a chemical equation. We will go through some more examples so that we can get used to balancing a chemical equation. Let us now go to the next one. Balancing some equations. We see that we have been given barium chloride reacting with aluminium sulfate to give us barium sulfate plus aluminium chloride. If you see, the equation is not balanced. So what we will do is try and balance the entire equation. Let us first take the sulfate molecule. The sulfate molecule has 3 of its atoms or 3 of its elements on the left hand side. So we will start our balancing by balancing the sulfate molecule. So balancing sulfate first. As there are 3 on the left hand side, we can add a coefficient 3 towards the right hand side. So to BaSO4, you can add a coefficient 3. This will act as 3 for barium and as for sulfate, as this 3 is 3 for the whole molecule of barium sulfate. As we see, the maximum number of atoms were in sulfate, so we first balanced sulfate. We will now balance aluminium. Aluminium had two of its atoms on the left hand side but only one on the right hand side. So we add a coefficient of 2 on the right hand side, making it 2AlCl3. Hence aluminium is balanced. We now balance barium, since we see that our chlorine will automatically be balanced as we balanced our barium. Barium had 3 atoms on the right hand side since we added 3 BaSO4. All we need to do is add a 3 towards the left hand side. Now if you see, there are 3 barium atoms on the left hand side and there are 3 barium atoms on the right hand side. Let us cross check the entire equation to see if the whole equation is balanced. Let us first take barium. Barium has 3 atoms on the left hand side, 3 atoms on the right hand side. It is balanced. Let's take chlorine. 3 times 2 is 6. Hence, there are 6 atoms on the left hand side. 2AlCl3. 2 times 3 is also 6. There are 6 atoms of chlorine on the right hand side. The equation is balanced, since aluminium and sulfate had already been balanced by us. Hence, the whole equation is balanced. Let us now go to the next one. Combustion of propane. Propane is a compound that contains usually atoms of carbon and hydrogen. If you burn propane, basically propane will react in the presence of oxygen and it will give us 2 compounds, carbon dioxide and water. We will first have to write the equation since the equation hasn't been given to us. So, the reactants that have been given to us are C3H8 plus O2. We will point the arrowhead in the direction of CO2 plus H2O. So, our equation will look like C3H8 plus O2 gives CO2 plus H2O. This equation isn't balanced, so we will begin by balancing the chemical equation. We will first balance the hydrogen atom, since you see that the maximum number is that of hydrogen. Hydrogen has 8 of its atoms on the left hand side and only 2 on the right hand side. Hence, balancing hydrogen. C3H8 plus O2 is CO2 plus 4H2O. Here on the left hand side we have 8 atoms and on the right hand side now 4 times 2 being 8 is we have 4 atoms. Let us now balance oxygen or carbon, since carbon has more number of atoms than oxygen. So balancing carbon next. C3H8 plus O2 is 3CO2 plus 4H2O. We saw that there were 3 atoms of carbon on our left hand side and only 1 atom of carbon on the right hand side. So to make the atoms equal, we were to add a coefficient of 3 just on the left of CO2. So now our carbon is balanced. Let us balance oxygen next. We see that the amount of oxygen now on the left hand side is 3 times 2, that is 6 atoms from CO2 of oxygen and 4 from the water molecule. So we have 10 in total. We have to balance the equation by having 10 on the left hand side also. So what we can do is add a coefficient of 5 on the left hand side of O2 and our equation will thus be balanced. And the equation, hence, the balanced equation of combustion of propane goes like C3H8 plus 5O2 gives 3CO2 plus 4H2O. It means when propane combines with 5 molecules of oxygen gas, it gives 3 molecules of carbon dioxide and 4 molecules of water. This equation is hence balanced. Let us take another example. Why are we discussing so many examples is because balancing a chemical equation plays a very important role even when we are writing our basic calculations for molecules, for volume, for mass or different other relations. So the next equation that has been given to us in the form of a word is sodium reacts with water to give sodium hydroxide and hydrogen gas is involved. Since the equation is not given to us, we will try and form the equation. Sodium, that is Na, reacts with water, that is plus H2O, to give sodium hydroxide, which is NaOH, plus hydrogen gas, which is H2. 1. Writing the chemical equation. So Na plus H2O gives NaOH plus H2. Let us balance hydrogen first, since it has the most number of atoms. We have 3 hydrogen atoms on the right hand side and 2 on the left hand side. So what we can do is add a coefficient of 2 on the right hand side and on the left hand side. Why? Because we need the smallest value. We need all molecules in their smallest ratios. If we wanted, we could have made them have 6 atoms on the right hand side and 6 atoms on the left hand side, but then the equation would be balanced, but it would not be in its smallest term. All atoms must be balanced and they must be there in their smallest ratio. Hence the smallest here that we could make them to be equal, the smallest number that we could use was 4. Hence we added a 2 as a coefficient on the left hand side of H2O, and then we added a 2 on the left hand side of sodium hydroxide, which had us give 4 atoms of hydrogen on the left hand side and 4 atoms of hydrogen on the right hand side. Now let us balance oxygen, but we see that oxygen is already balanced. While we were trying to balance hydrogen, we accidentally already balanced oxygen. If we were to cross check, let's see, there are 2 atoms. Since there is H2, 2 H2O, so there are 2 atoms of oxygen on the left hand side, 2 NaOH. The atoms of oxygen are also 2 on the right hand side. So oxygen is already balanced. All we need to do now to balance the entire equation is balance sodium. To balance sodium, we need 2 atoms of sodium on the left hand side, as there are already 2 atoms of sodium on the right hand side. So balancing sodium will lead us to the formation of the equation 2Na plus 2H2O gives 2NaOH plus H2. All we did was add a coefficient 2 to the left hand side of Na. If you see in all the examples, we never changed the ratio of the atoms that were at the bottom. All we changed were the ratio of molecules, that is the ones that are represented by a bigger number on the left hand side. This equation is now balanced. So a balanced equation of sodium reacting with water to give sodium hydroxide and hydrogen gas can be written as 2 atoms of sodium reacts with 2 molecules of water to give 2 molecules of sodium hydroxide and 1 molecule of hydrogen gas. That is it for this chapter. Let us now study what all we did in this chapter. We know that law of conservation of mass dictates that all chemical equations be balanced. So the number of atoms of each element on the reactant side must be same as the number of atoms of each element on the product side. Why? Because we know that mass is something that can neither be created nor be destroyed in a chemical reaction. Valency is something that is termed as combining capacity of an element. We judge it by seeing the number of electrons an atom can gain or the number of electrons an atom can lose. Why do we only see electrons is because protons and nucleons are something that are present in the nucleus of an atom, and a nucleus of an atom, all the protons and neutrons are something that cannot go and be taken away from that nucleus. Electrons, on the other hand, are present on the outer shells of an atom and they are revolving around that nucleus. They are something that can be taken away or can be gained. Hence, valency is seen by how many electrons one atom can gain or how many electrons one atom can leave. Elements can either be monovalent or divalent or trivalent. It means either they can gain or lose 1 electron, either they can gain or lose 2 electrons, making them divalent, either they can gain or lose 3 electrons, making them trivalent. 2 examples that we discussed that were of copper and iron, they can have variable valency. It means sometimes they can lose 1 or 2 electrons in terms of copper, or sometimes they can lose 2 or 3 electrons in example of iron. Valency helps us make a formula unit. To balance a certain chemical equation, we write the given equation first if it is not given to us. From the word equation, we form a chemical equation if we know the symbolic representation of each element. We now choose the element with the maximum number of atoms. It does not matter, it is either the reactant side or the product side. Then we balance this element. We then go to the next element with the maximum number of atoms, and we keep doing the balancing until the whole equation is balanced. The last step includes cross-checking the entire equation by counting the number of atoms of each element on both sides, and thus we form a balanced chemical equation. I have discussed more than 3 examples with you of how to balance different chemical equations. I hope all of them have been clear, and that has all been that is for this session. In the coming session, that is the next session, we will now see how we can make this balanced chemical equation more informative. We will see whether the reactant that is there is a solid or a liquid, or the product that is formed is a precipitate, either it's a gas or either it's a solid, either it's a liquid or either it's an aqueous solution. How we can write them and how we represent them is something that we will study. We will then study what balanced chemical equations tell us. What can we interpret through balanced chemical equations? Then we will discuss 2 different numericals from your